Hi everyone, my name is Leah and I'm a data scientist at Fiddler, and as Aaron said, I'm going to talk about machine learning fairness, and especially I'm going to introduce you to intersectional group fairness. For those of you who don't know Fiddler, a quick introduction. We believe that every AI solution should be responsible and ethical. So with the mission to help every organization build trust into AI, we have developed a model performance monitoring platform, and this is powered by explainable AI. So our platform empowers data science and engineering teams to track and troubleshoot machine learning issues, such as drift and integrity, for example. And you can do this faster with our unique XAI technology. So the XAI not only pinpoints causes of the performance drops, but it also enables our user to quickly and easily validate and compare different models and detect bias. So in this session today, we'll go over our approach to detect bias, which is using what we call intersectional group fairness. So the first question everyone should be asking is why fairness is important. Well, maybe you have been hearing about the latest, for example, European Union regulation and its emphasis on the trust in AI. So there are many elements that account toward trust, and fairness is one of them. So the question is, how do you detect and mitigate bias in your AI models to avoid, a bad experience? For example, I don't know if you heard about it, the Apple Card got investigated after gender discrimination complaints, or again, JP Morgan's that settled federal motor discrimination suit for $55 million. So machine learning models are often biased, and this can be due to a variety of complex causes like pre-existing societal bias, an imbalanced training data set, etc. So for example, there are software used across the nation to predict future criminals, and those software have a strong racial bias. So for example, it has been found in 2016 that Compass, which is the algorithm used for recidivism predictions. This algorithm produces much higher false positive rate for Black people than for white people. And risk scores like this one are incredibly common in courtrooms across the nation. So they're used to inform decisions about who can be set free at every stage of the criminal justice systems. So here, you have, two persons both at one prior offense, and on the left you have the one man who got like 3 subsequent offenses, but the algorithm gave him like a low risk score of 3, and on the right side you have a Black man who had no subsequent offenses but got a higher risk score of 10. So the question is, would you trust such faulty system? Okay, so with that in mind, let's talk about what is intersectional group fairness. So intersectional fairness is fairness along overlapping dimensions, so including race, gender, sexual orientation, age, disability, etc. So it's not just binary protected class versus unprotected class. It's really like taking into account multiple dimensions. And why this is important? Well, let's consider, this a doom example here. It's a binary classification model that that predicts if a person is going to pass or fail. Okay, and here we can see equal number of Black and white people that pass, and similarly, you can see equal number of men and women that pass. So we can think like this classification is fair. But however, if you take both gender and race together, you can see none of the white men and none of the Black women pass. This classification is still, unfair. So that's why considering intersectional fairness is an important point. And we came up with a framework to measure fairness in this, intersectional way. And this is what we call the worst case disparity framework. So you can find more details in the paper that we wrote with Avijit, which is from Northeastern University, and Mary, which is another data scientist at Fiddler. But to give you an idea, basically, the framework is the following. So it's what we call a Rawlsian principle of distributive justice. So first step, you're going to select a fairness metric. Then you're going to compute this fairness metric for each subgroup. And when I say subgroup, if we take again the same example than before, and we have both race and gender as protected attributes, one subgroup will be, a Black woman, another one will be Black man, etc. So you compute this fairness metric for each of the subgroups. And then to give you an idea about how the model is performing, and is it like, do you have disparities among your subgroups? You compute what we call the min-max ratio, which is just taking the minimal value that you obtain by the maximum value. And the idea behind the min-max ratio is that we want to achieve like a ratio close to 1. Because, if that's the case, it means like your minimum value and your maximum value are, very close to each other. But it also means that all the subgroups have similar values for the selected fairness metrics, and so that you don't have disparities for this fairness metric. So this is the global framework we came up with. And so how, when, and where can we use intersectional fairness to improve our AI solution that comply, with regulation and build trust in AI? That's the question. So recently, we introduced what we call a model performance management framework, which suggests that, establishing a feedback loop in the machine learning lifecycle to help data scientists improve models more efficiently. So you probably are familiar with this diagram where, you have offline step where you train and validate your model. And then you go into online where you deploy into production your model. You want to monitor or, observe performance drift, outlier, bias, etc., and analyze those results. So in short, the model performance management is a framework that establishes a feedback loop in the machine learning lifecycle. So you're always ready to receive feedback from machine learning models in production to troubleshoot faster and improve performance. So basically, when you're in step 5, maybe you want to retrain the model and you go back to step 1. Okay, now imagine adding fairness to this model performance management. And so throughout a model lifecycle, you will continuously and cautiously measuring bias in the model to always be responsible. So you want to train and validate your model and, both look at fairness at those steps. But when you go online and you deploy your model into production, you still want to monitor for fairness and analyze the results. Why? Because fairness, a model can be biased later after being deployed into production. So that's a very important step. Okay, and this last part of the presentation, I wanted to give you a little bit of a preview of what we have as our bias detector. So we do have this framework, and I don't know if you're familiar, but you have a lot of different overall fairness metrics that exist in the literature today. So we decided to select 4 key group fairness metrics that we think are widely used and that have an effective coverage. So those are disparate impact, demographic parity, equal opportunity, and group benefit. And to give you an idea a little bit, so disparate impact is a form of indirect and intentional discrimination in which certain decisions disproportionately affect members of a protected group. And very similarly to disparate impact, you have demographic parity. And we decided to put both. I personally think demographic parity is easier to interpret, but you have to know that disparate impact is the only metric currently that is codified in US law. So it's also important, I think, to have disparate impact. But so basically, based on the same measure that disparate impact, you have demographic parity that compares if the proportion of each segment of a protected class receive the positive outcome at equal rates. Then we have equal opportunity, which is based on the true positive rate. And it means that all people should be treated equally or similarly and not disadvantaged by prejudice or bias. And then finally, we have group benefit, which aims to measure the rate at which a particular event is predicted to occur within a subgroup, compared to the rate at which it actually occurs. Okay, so with that in mind, we have those, 4 key group fairness metrics. We do have this intersectional fairness that I talked about. So here on the top, you can see I selected gender and race as protected attributes. And we do have our novel framework from our research paper to assess group fairness across protected classes. So here, as an example, you have equal opportunity. So if you look, the bar chart represents the equal opportunity, so the true positive rate value for each subgroup. And then in green, you have the min-max ratio, which is taking the minimum by the maximum value. A good rule of thumb is to consider that we usually use is like below 0.8. You may consider that you have some disparities among your subgroups for your model. So here 0.9 is doing pretty good. So in addition to those fairness metrics, we also add what we call data set metrics. So it's a pre-modeling check to make sure we didn't introduce some possible bias with the data. So for example, here my predicted features are gender and race, and I didn't include those in my input features, right? But I want to check if those two are highly dependent with another feature that could carry over the bias. So here in this page, we decided to display mutual information. So mutual information gives information about existing dependence in your data set between the protected attributes and the remaining features. And here we are actually displaying a normalized version of mutual information. Like this, you have a symmetric metric that has values between 0 and 1. And 1 meaning perfect dependencies and 0 no dependencies. So here I can see like gender and race are not dependent with, highly dependent with any other input features. So I can be sure that's not going to happen. And in addition to dataset metrics, we also display model performance metrics. So for example, for binary classification models, we do have like true positive rate, true negative rate, etc. We have more of those. And the idea is the same. You compute those metrics for each subgroups and you compare the values for a given metric among all the subgroups. You want similar values. So, as I mentioned, the ultimate goal is to have real-time fairness. So measuring fairness on production data as well as on the static data set. Then you want also to integrate into monitoring. So we'll receive real-time fairness alerts and address the issue when they matter. And another thing we are also thinking is like having a built-in explainability. So to understand the impact of features to specific fairness metrics. And finally, it's we want risk mitigation, so track back to any past incident or analyze feature prediction to minimize the risk. So yeah, that was it for me today. I know we only had like 15 minutes today and we didn't have time to do, you know, proper demo or whatever, but if you're interested, I'm happy to do so. So please reach out to me by email.